simulating a simple RISC CPU in C, fetch, decode, execute. We start by defining constants for memory size, number of registers, and maximum program size. Then we define instruction codes using define macros for readability. Each instruction is represented by a number. For example, load is 1, store is 2, and so on. Next, we declare 4 registers, a 64-location memory, a program counter, PC, and an instruction register, IR. We'll also create a sample program with 5 instructions. This program will load 2 values from memory, add them, and store the result. We also define the initial values in memory. Memory 1 is 5, and memory 2 is 10. Now comes the heart of the simulation, the while loop that mimics the CPU cycles. For every cycle, we fetch the instruction from the program using PC, decode it into the IR instruction register, execute it using a switch statement. Each case corresponds to one instruction. For example, the load case copies a value from memory into a register and adds values between registers. After each instruction, we print the current state of the system using this function. It shows the cycle number, PC, the current instruction, values in registers, and what's in memory 15th. When we run the program, it should display the state for each cycle. At the end, the sum 15 is stored in memory 15th, and we halt execution. To summarize, this C program simulates a simple CPU with basic instructions. In this program, we simulate how a direct mapped cache works in a computer system. The cache is built using a structure called cache block, and the cache class manages its behavior. The user can set the cache size and block size, and the program keeps track of instruction and data accesses, including hits and misses. During execution, we initialize 3 128x128 matrices and simulate a matrix multiplication. For each memory access, whether it's fetching instructions or accessing matrix data, the cache logic determines whether it's a hit or a miss, updates the cache accordingly, and calculates the total execution time and average memory access time.